Okay, this video is for the angular momentum and its conservation NMSI packet for your response key. So let's go ahead and get to it. This will be question 1. It says, an ice skater starts her performance ending spin with her arms outstretched, rotating at 2.5 revolutions per second. As she pulls her arms inward, her rotational inertia decreases to 0.7 of its original value. So that's, her moment of inertia is going to decrease by a value of 0.7. So that's what's key. So what we can write with that is we can say that her final rotational inertia is equal to 0.7 times initial. This is going to be key throughout this problem. All right. So that's just from reading it. This is going to be, let's see what it wants here. All right. So what's her final angular speed? So what we need to do is write our conservation of angular momentum, where the angular momentum before is equal to the angular momentum after final. So I have, remember that L equals I omega, just like linear. So I have initial equals final. All right. So they give us the initial here. Our initial velocity is 2.5 revolutions per second. So we know that. They give us, we want to find her final velocity. So let's go ahead and solve for that. So I'm just going to divide over. So I get final velocity is equal to initial. Well, what I do know is this, that her final moment of inertia is equal to 0.7 this. So I can plug this in. Final equals initial 0.7 initial. These cancel out. And I'm left with 0.7. So when I do that, 0.7, I get what? 0.57. All right, so all I did was I plugged this in for that and then solved. All right, so again, the key was this right here. That's the key. What is the ratio of her final kinetic energy to her initial kinetic energy? So I'm going to clear this. B, it says final compared to initial. We want this ratio. What's that ratio? So let's go ahead and look at this. We remember rotational kinetic energy is equal to 1/2 angular velocity squared. Final, so let's go ahead and just plug into this right here. So our final would be 1/2 IF final squared over 1/2 I initial omega initial squared. All right, all I do is plug in basic equation, and then we have to remember that moment of inertia final from the problem is equal to 0.7 moment of inertia initial. All right, has cancel out. Then what we got here is we're going to do the same thing. This is going to plug in here. So I get 0.7 initial omega final squared over initial squared. Out, I get 0.7 times final was 3.57 squared over initial, which was 2.5 squared. Doing the calculator, you get a ratio of 1.43. Okay. All right, so pretty straightforward, kind of the same thing. Again, the key was this right here, knowing that, and then knowing your basic kinetic energy equation. All right, let's keep going here. C says, if the ratio between the kinetic energy and the initial kinetic energy is less than 1, where did the energy go? Oh, it was greater than 1. If the ratio is greater than 1, where did the extra energy come from? So what it's saying is she has more final kinetic energy than she does initial kinetic energy. And how that happens is, if you watch skaters, they always start with their arms out wide, and then they go to bringing their arms, tucked in. Okay, so they do amount of work when they bring their arms in. So that work increases the energy, and therefore that's where that extra energy comes from the final position. Okay. All right. Let's see. All right. Question 2. We have a little spoon, a big spoon. Got a belt going around. This will be 1. This will be 2. All right. They're both spinning this way, and they both have radiuses of r. 2 wheels shown above are connected by a belt. The belt does not slip. The belt does not slip. That's key. All right. As the wheels rotate. Wheel 2 has a radius 2.5 times larger than radius of wheel 1. So that's what we know right away. So we know that R2 is 2.5 times R1. I don't know why I made that an I. So that we know that from the problem, okay? So A says, what would the ratio of I1 over I2 be equal to if both the wheels had the same angular momentum? All right? So key here is this. We have to, so what the ratio, okay, so what we know is, since the belt does not slip, the velocity of 1 has to equal the velocity, right? And we know that linear velocity here is equal to r. So I have r1 omega 1 equals r2 omega 2. All right? And in this case, what do I got? I know R2 is equal to this, right? So I'm going to basically plug that in here again. R1 omega 1 equals 2.5 R1 times omega 2 on the second wheel. All right? What's going to happen here is the radiuses are going to cancel out, and I get that the speed here. So when I cancel this out, I get omega 1 is equal to 2.5 times omega 2. So now I know the velocities, right? If they want me to compare moment of inertias, but they have to have the same, if they have the same angular momentum. So what that's saying is it has the same L1 has to equal L2. All right, saying if what will the ratio of I's be if they have the same angular momentum. All right, so if I expand this out, I remember that 1 equals 72. So I want to get this ratio here, right? And the problem, it says I1 over I2. That's what, so I'm going to divide this over here and divide that over. So I get I1 I2 wanted equals. I'm dividing that over, so I get 2 over omega 1. Well, I know that omega 1 equals that, so I got omega 2 on the top. Take this right here, plug it in there, I get 2.5 omega 2. So the ratio you get is 1 over 2.5 or 0.4. All right, clear that out. Well, let me erase, because we're going to use some of this for the next one. Now we're going to use that, so let's clear this out right here. You're going to do a different ratio. Yeah. Right. All right. Now it says, what would the ratio, same ratio, be if both wheels had the same kinetic energy? So instead of L1 equaling L2, it's going to be K1 equals K2. Our equation for kinetic energy here is 1/2 1 omega 1 squared equals 1/2 2 omega 2 squared. So again, halves cancel out right away. I'm going to get the ratio, so I divide over. I get I1 over I2 equals omega 2 squared over omega 1 squared. Go ahead and enter that in. So I got omega 1 again. I'm going to plug in. So I get omega 2 squared equals 2.5 squared times omega 2 squared. So if you do this out, those cancel out, and you're going to get 1 over 6.25. That's 2.5 squared, which equals 0.16. Pretty straightforward so far. Oh, that's it for that one. All right. So we're on to a new problem. So the key was this: is you had to start with this right here, because it told you that. And then in the last problem, it said the angular momentums were equal. So if you can start with this and then go from there, that's just how you do those problems right there. 3. All right. So we got a metal rod pivoting about one end. Yeah, so we can find, okay, I'm sorry, I was just reading it just to see what they give us. Metal rod of mass 5 kilograms in length, 2 meters, is attached to a pivot point at top of the rod. The rotational inertia about this pivot point is 1/3 ml squared. So they give you the equation there. A 0.35 kilogram rubber ball hits the rod with a speed of 15 meters per second at 1.5 meters away from the pivot and bounces off with a speed of 10 in the opposite direction. What is the angular momentum of the ball rod? What is the initial? Okay, sorry. So what is the initial? Well, initially, the only thing that's moving is the ball, and it's a point mass. And we know that from the picture, the ball is going to be coming straight in, so it's perpendicular. So we know the angle that it makes with the rod is 90 degrees, right? So when we look at our angular momentum for a point mass, I get R mv sine theta. Well, if I do sine of 90, that's just 1, so I get R mv is going to be my initial, and I know that L of the rod is going to be 0 initially because it's not moving. So if I plug in here, the R it is 1.5 meters away from the pivot point. The mass of the ball is 0.35. And what else I need? V, it's traveling at 15 meters per second, which gives me a angular momentum of 7.875 kilograms per square seconds. straightforward, and since the rod's zero, that's the total initial. Okay, that one was pretty easy. So let's keep rolling here. Clear that up. What is the angular speed of the rod immediately after the collision? All right, so here we're going to do conservation of angular momentum equals 5. Right? So remember we said we already found the initial. We can actually just write that in, but what I'll do is I'll write angular momentum of the ball initial. Well, there's two things moving afterwards, right? The ball's going to be moving and the rod's going to be moving. So I got L of the ball final plus L of the rod final. I can plug in. That's the equation I used here. Rm the initial equals Rm the final plus angular momentum of a rod is going to be moment of inertia times the angular velocity. Well, we have to calculate the moment of inertia. It's 1/3. Is it ml squared? Yep. It's right about the end. Yep. And equals 1/3. Mass of the rod is 5. Length of the rod is 2 squared. You get inertia of, where's it at? All right, I put it there. 6.67 is what we get. Let me do it real quick. 4 times 5 times 1 divided by 3. Yeah, 6.67. All right, so use that in there. So if I solve this for W, right? If I solve this for W, that's what I want. The angular speed of the rod. I get. I gotta subtract it over, so I get RMVI minus RMVS all over I. Numbers in here. I already know that's 7.875 minus the radius is still 1.5, except now, so the mass of 0.35, but it said it's going 10 meters per second in the opposite direction. So if 15 was positive, that means 10 has to be negative. All over moment of inertia of the rod. In your calculator, you're going to get final velocity of the rod, 1.97 radians per second. Good. All right. Yeah, you're going to need this velocity, so let's just get onto it. So let's clear this up, and let's go to C. So it says, is this an elastic collision? So what we need to do is remember what the definition of elastic collision was, because there was 3 of them. There's elastic, inelastic, and perfectly inelastic. Them, momentum is conserved. All right, all of momentum is conserved. Elastic, KE is conserved. Inelastic, KE is not conserved. Perfectly inelastic, KE is not conserved, and they stick. All right, so that was just kind of a refresher here. So if it asks us, is the collision elastic? We have to see, well, we know momentum is conserved, we just used it, right? So what we need to do is see what's going on with the kinetic energies here, all right? So what we can do is, let's find the initial kinetic energy. How many things are moving initial? Just once, it's the ball. straight line, so we can use linear kinetic energy, right? The linear equations here, 0.35, it had a velocity of 15. So my initial kinetic energy for the system is 39. All right, final. You saw the ball, right? So kinetic energy ball plus kinetic energy rod equals kinetic energy pound. So ball is going to be 1/2 mv squared plus omega squared. And that's going to be the kinetic energy final. What was the velocity? It's -10. Don't matter. It's negative squared plus 1/2 6.67 omega. We got it to be 1.97. Oh, fill that up. Kinetic energy final is going to equal 30.4. That's annoying. Get out of here. 30.4 joules. All right. So from this, we get that kinetic energy initial is greater than kinetic energy final. So we've lost some energy here. So if we've lost energy, kinetic energy is not conserved. So no, this is not elastic. Pretty straightforward. Hope that helped. That's it for this video.